Our second keynote lecturer from the Professor Kunpeng. He is a director of engineering structural reinforcement and restoration institute in CCCC Third Harbor Engineering Company Limited. He is also professor of civil engineering materials. Professor Gu's main research interests include the concrete crack control of the engineering structure, durability of the concrete structure, development and application of the new building materials. He involved in more than 10 national key construction projects, such as the Hong Kong-Zhuhai Macao Bridge, Yanshan Port, Taihu Tunnel, Beijing-Shanghai High-Speed Railway, and related technical researches. He is the fourth city star Youth Talent Development Program of the Shanghai Urban and Rural Construction and Transportation Outstanding Youth Winner. So today, his presentation title is Concrete Crack Control Technology and its Application in Super Large Cast-in-situ Tunnel. Yes, which would introduce us the leading edge technology in the concrete construction in China. So Professor Kunpeng, please provide us.
Greetings, dear experts, scholars, engineers, ladies and gentlemen. I am Kunpeng from China Communications Construction Third Harbor Engineering Company. With the rapid development of infrastructure construction in China, the engineering technology has also made some great breakthroughs and innovations. As a Chinese engineer, I am very honored to have this opportunity to share relevant experience with you. The subject of my report today is technology and application of concrete crack control in super large scale cast-in-place tunnel. My report mainly contains the following contents. As for the super large scale cast-in-place tunnel, the design requirements for the structure form, construction environment, and the technologies are very special. The concrete is easy to cracking under the action of multiple factors, such as the asynchronous shrinkage and the temperature stress. So I will analyze the problems of cracking and the causes of this phenomenon firstly. In the second part, I will summarize the theoretical and the technological developments related to crack control of this structure by using the knowledge in it as a reference to help us to solve the cracking problems. On this basis, from a philosophical point of view, we will think about how to control the cracks more naturally and efficiently. Chinese engineers' concept of concrete crack control will be put forward. After that, in the third and fourth part, I will share with you two representative projects in China that I have experienced. These two projects fit well with the theory and the philosophical thinking in the second part. The technologies and applications of concrete crack control in the super large scale cast-in-place tunnel of these projects will be introduced. Through engineering practice, the technologies were proved to be reasonable and effective. At last, I will give you a conclusion of my report and share my opinions about the development of concrete crack control technologies in the future. First part. Concrete cracking problem in super large scale cast-in-place tunnel. Nowadays, super large scale, ultra long service life, complex construction technology, and device-fied materials are the developing directions of tunnel construction. Tunnels in cast-in-place concrete structure are frequently used in large projects. As the figure shows the Century Project Hong Kong-Zhuhai Macao Bridge, constructed from 2009 to 2018, took nearly 10 years. The project's cast-in-place tunnel is a typical representative. The width and the height of this cast-in-place tunnel are respective 72.2 meters and 11.4 meters. Its designed life is 120 years. Various materials and construction technologies were used in this tunnel. Although the larger size of tunnel structure brings comfort and convenience to us, a great technical challenge is coming too. The challenge is concrete cracking problem during the construction of the super large-scale cast-in-place tunnel, which is one of the global major engineering problems. The problem has plagued us for a long time. This problem occurs not only in the cast-in-place tunnel, but also in the large ship locks and dock projects with similar structures. It's very difficult to control the cracks of this kind of infrastructure. The difficulty is much higher than that of general large-scale industrial and civil buildings, and the losses caused by the cracks are more serious. I will explain this in detail in the following analysis. As is shown in the figure, the main crack pattern presented by this structure, we use red lines to show the cracks and the construction joints. In a single pouring section, above the horizontal construction joint, a vertical cracking appears on the side wall every 1 to 3 meters, and its distribution is relatively uniform. The length of crack gradually decreases from the mid to the sides, and the diagonal cracks appear due to the shear stress on the both sides. As we all know, once concrete structure cracks, it will affect its function. If the structure is in a water-rich environment, leakage will occur. When penetrating cracks appear, it will reduce the stiffness of concrete structure. Furthermore, cracks will also affect the durability of the concrete, especially in the underwater tunnels. Once the tunnel cracks, the chloride ions, which is the main corrosive medium, will accumulate on the face of the steel bars along with the seawater. As a result, the steel bar will be corroded, and the entire structure will be destroyed at last. For the super large-scale cast-in-place tunnel, as a major national infrastructure, its environment is severer and more complicated compared with the industrial and civil construction structures. Bigger size and more serious problems will cause deeper loss. So, it is urgent to control the cracks of such tunnel structures. Before we try to fix the problem, we need to ask ourselves several questions. Why the cracks occur? What is the difference between this type of crack and the cracks of other structures? What makes it so difficult to control? Through analysis, one reason of cracking is asynchronous shrinkage. As the figure shows, for cast-in-place tunnel, the traditional vertical step-by-step pouring process is divided into 2 or 3 steps. The pouring of sidewall is always in the last step. We all know that the concrete mixture shrinks during the setting and the hardening process. If the time interval between pouring steps is small, the difference in shrinkage between the bottom slab and the side wall is also small, just like the concrete pouring in industrial and civil construction. But the key point is, during the construction of super large-scale cast-in-place tunnel, the limited working environment and the complex process makes the time interval very long, and the average value is 1 month. The figure of long-term shrinkage test of concrete shows that the shrinkage is basically over after 1 month. So, a synchronous shrinkage of concrete poured before and after is huge. The asynchronous shrinkage leads to restraint, and the restraint between bottom slab and the side wall will cause stress and the cracking. Another reason of cracking is temperature strength. The super large-scale cast-in-place tunnel belongs to mass concrete. When the concrete hydrates, it will generate lots of heat. The temperature will change drastically. For example, as is shown in the temperature curve after concrete pouring. In the early age, the temperature of concrete increases rapidly. After 30 days, it will approach the room temperature. During the tunnel construction, due to the out-of-sync pouring, the temperature difference between the bottom slab and the side wall is large. As a result, their volume changes differently. At the construction joints, the thermal expansion or contraction of the side wall is restricted by the bottom slab. Then, tensile strength appears, finally leading to concrete cracking. For the concrete of the super large-scale cast-in-place tunnel, the asynchronous shrinkage and the temperature stress are the main reasons for the cracking of the structure. In addition, there are some common and minor reasons for cracks in concrete structures. I will give a brief introduction to these reasons. For example, the basic concrete properties and the internal defects. The low tensile strength and the brittleness of concrete is not enough to resist the cracks. As a figure of tensile stress, strength-constitutive relation, and the ultimate strength of tension shows, the internal defects are cavities, porosity clot, and bubbles, etc. These shortcomings will be amplified under the effect of main reasons. Other minor reasons that may cause the structural cracks include raw material and mix ratio of concrete, design flaws, bad construction quality, and poor usage conditions. Most of cracks caused by these reasons can be solved by human intervention. There's always a group of people that are not just satisfied with discovering problems, they are also eager to grasp the laws. They put forward relevant theories and technologies that offer guidelines for us to control the cracks in the super large-scale cast-in-situ tunnels. I will introduce this theory in this part, and on the basis, it will be raised to the head of philosophical thinking and gradually formed the engineer's concept of crack control. Paths are made by people. Professor Wang Tiemen has been exploring the road of concrete crack control for nearly 60 years. He has put forward many crack control theories of engineering structure. The following is a brief introduction to the calculation theory of shrinkage strength and the temperature strength for long wall on bottom slab. In this theory about shrinkage stress, in order to analyze the shrinkage stress distribution of long concrete wall on bottom slab and control cracks, a simplified calculation formula on shrinkage stress of long wall was presented. This page shows the deduction and calculation of formulas. These theories considered the bottom slab's influence on the wall and treated separate piles foundations as springs by stiffness averaging method. In the single layer slab column wall structure shown in the figure, the long wall was simplified into elastic foundation rods, and the interaction between the wall and the bottom slab was analyzed. This page also shows the calculation formulas of axial force and bending moment. The theory points out the bottom slab has an important influence on the shrinkage stress of the wall. Greater the rigidity of bottom slab, more obvious of the influence. The effect of bottom slab must be considered when analyzing the shrinkage stress. In general, shortening the wall length has effect on reducing the shrinkage stress. In this theory about temperature strength, as the figures show, calculation model about force and deformation of the wall and the bottom was proposed. Furthermore, simplified calculation formulas on restraint strength of the wall, shear strength between wall and the bottom slab, spacing of the expansion joint were deduced. The result of theory shows when the slab wall stiffness ratio increases, the maximum tensile strength of the wall increases rapidly. Its distribution tends to be uniform along the length, and the crack spacing tends to decrease. From no dam no cracking to no dam cracking. Academician Zhu Bofang, the pioneer of mass concrete thermal strength theory, shows us his unique comprehension of crack control. This theory emphasizes that the motive power of concrete cracks is thermal stress, not just temperature. Controlling temperature stress is the way to prevent concrete cracks. Concrete cracks occur because the tensile stress exceeds the tensile strength, and the generation of tensile stress is not only related to temperature but also related to constraints. The super large-scale cast-in-place tunnel is a mass concrete structure. We need to pay attention to the thermal stresses. This theory tells us how to calculate thermal stress, how to control temperature field, and how to reduce restraints. One method is to use the cooling water pipe, as the right figure shows, to accelerate the heat dissipation and reduce the temperature inside the concrete. Water pipes are embedded in concrete, and cold water is passed to cool the concrete after pouring. Calculation method of it is also mentioned. At the construction site, cooling pipe plays a positive role in concrete temperature control. Foreign scholars have also conducted numerous studies on the control of concrete cracks and have reached very good conclusions. In Harrison's report, Early Age Thermal Crack Control in Concrete, he got some useful conclusions. For example, when the restrained thermal contraction strain exceeds the tensile strain capacity of concrete, early-age thermal cracking occurs. The restraint to thermal moment is the product of the coefficient of thermal expansions of the concrete. The temperature fall from a peak during thermal hydration and the restraint factor. The concrete temperature rise is shown to depend on a number of factors: thermal content, type of aggregate, possible use of thermal replacement materials, as well as the ambient temperature, formwork used, and section thickness. Restraint is a function of the construction sequence and the constraint of several elements. In ACI report on thermal and volume change effects on cracking of mass concrete, it mentions that the cracks can be controlled if the temperature history and temperature distribution within the volume of concrete could be maintained in proper values, and if concrete can be supported without restraint, or supported on older concrete expanding and contracting in the same manner as the new concrete. Apart from analyzing and summarizing research theories at home and abroad, we also conducted in-depth thinking. In an ancient Chinese philosophy, Tai Chi, it tells us everything has two sides. They are opposite and unified, and can be merged and transformed. We get inspired by Tai Chi. During the process of concrete crack control, there are also exists Tai Chi. They are resistance and release. Resistance means improve the tensile strength or ultimate tensile stress, using tensile deformation for energy absorption. Release means reduce strength and deformation caused by restraint. Use deformation or displacement for energy release. We can either use the two methods separately or together. So, based on the theoretical research and the philosophical thinking, Chinese engineers have gradually formed their own concept of crack control. Here, I will give you some examples about how to use resistance and release. In terms of resistance, we use new anti-cracking materials to strengthen the crack resistance of concrete. These materials can be super-absorbing polymers, polypropylene fibers, shrinkage-reducing agent, and nanomaterials. In terms of release, we use crack inducer to fabricate man-made cracks. These cracks play a role in releasing energy, avoiding concrete cracking naturally. At last, we combine the concept of resistance and release together. Alternative bay construction method was formed. Using this method, we need to release the stress of concrete at early age. Use the tensile capacity of concrete to resist concrete cracks at late age. Release first, resistance later. As the right figure shows, the alternative bay construction method divides the building foundation into several areas and constructs according to the principle of block planning, block construction, layered pouring, and integral molding. It's like checkers, that is, pouring one section at intervals. To avoid the drastic temperature difference and the drying effect in the initial stage of concrete construction, the interval between two adjacent sections is not less than 7 days, so that there's no need to leave the post-pouring joint. In the following content, I will take two mega projects in China, the Hong Kong-Zhuhai Macao Bridge and the Taihu Tunnel, as examples, based on the theory, technology, and the philosophy about resistance and release mentioned before. And I will share the research and the practical application of concrete crack control technologies. The first case, the Hong Kong-Zhuhai Macao Bridge. The cast-in-place tunnel of Hong Kong-Zhuhai Macao Bridge locates in a marine corrosive environment. It will cause severe durability problems. It has an ultra-long design life of 120 years. The main structure size of the tunnel is max height 11.4 meters and max width 72.2 meters. It is a box-shaped mass concrete structure with the largest cross-section size among similar projects in the world, and it is very difficult to control cracks. The tunnel adopted slope excavation construction, and there were some special difficulties such as isolated offshore work environment, vertical step-by-step pouring, restrained by foundation and large section size. To control the cracks in this tunnel, we developed and applied multiple technologies. First, shrinkage crack control technology. When we use traditional pouring method, only by shortening pouring time interval to less than 21 days and making the segment length less than 12.5 meters, the cracks in the side wall can be eliminated. According to the actual construction, it was not feasible. So we improved the pouring method and achieved success. Our method was moving the construction joint upward, pouring the bottom slab and the side wall at one time. According to calculation result, when the segment length is controlled within 22.5 meters, it is feasible for construction. Combined with temperature control and reasonable curing, cracks can be greatly reduced. Another technology was temperature control technology of mass concrete. We used it to control temperature stresses. The left figure shows the calculation results of tunnel structure. We can notice that without any proper temperature control method, the max core temperature of concrete reached about 74 degrees in Celsius. To decrease the temperature, we tried to use cooling water pipe. The layout cooling water pipe is shown in figure at the bottom. To make the cooling water circulated smoothly in the water pipe, we developed a temperature control system of circulating cooling water that contains water container, water pump, water separator, and the flow controller, as the figure shows. As I mentioned in the shrinkage crack control technology, we improved the pouring method by pouring the bottom slab and the side wall at one time. The toughness in implementing this method is design assembling support of formwork. After many attempts, we used advanced formwork techniques and full house brackets for concrete pouring. At last, we finished concrete pouring successfully. The figure shows one segment of the tunnel after curing. Combining theory with practice, we used the alternative bay construction method in the construction of the whole cast-in-place tunnel, as the dynamic picture vividly shows. After a systematic study, cracks mainly caused by asynchronous shrink and temperature stress were effectively eliminated. As the figure about sidewall, bottom slab, and the roof shows, the crack is not occur. The segment of tunnel with length from 10.7 to 15.9 meters and 25.5 to 30 meters show no cracks in the side wall and the bottom slab. After the tunnel and the artificial island finished, the final effect of the tunnel concrete is very satisfied. Through this mega project, we achieved some conclusions and innovations. Innovatively, the construction joints were set on the top of the sidewall, so the sidewall and the bottom slab were poured as a whole at one time. Finally, the problems of cracks in the bottom slabs and the side walls of the tunnel were solved. Technical difficulties such as design assembly support of formwork, cutting vibration curving of concrete were solved when pouring the side wall and the bottom slab as a whole. The quality of concrete structure was ensured. Temperature control technologies of mass concrete were effectively used, and a temperature control system of circulating cooling water, which can be used in super large-sized tunnel, was developed. Case 2. The Taihu Lake Tunnel. Let me introduce you this super large-scale cast-in-place tunnel and its crack control technology. Taihu Lake Tunnel Engineering is #1 project of Jiangsu Province in 2018. It belongs to mass concrete structure. It will become the longest and the widest underwater tunnel in China. Strict requirements of durability, impermeability, and crack resistance was put forward. Due to vertical support and working environment, only traditional pouring method can be used. There exist special difficulties in concrete crack control of the tunnel. First, the size of tunnel is too large. The step-by-step pouring concrete is prone to stress cracks due to asynchronous shrinkage. And second, the environment of cast-in-place construction is uncontrollable and greatly affected by environmental temperature. To solve the special difficulties in concrete crack control, we developed a balanced system of concrete temperature field. This system uses the hydration heat of the newly poured concrete at the upper to heat the previously poured concrete at the bottom to realize the redistribution and the balance of temperature field. As the figure shows, first, connecting the water pipe between the side wall and the bottom slab, and then making cooling water circulate between the two parts. Through analysis, after using balanced system of concrete temperature field, the calculated concrete anti-cracking safety factor of side wall increased from 0.8 to 1.24 and meet the designed requirement. The side wall temperature was reduced by 15 to 20 degrees in Celsius, and the chamfer temperature was increased by 5 to 8 degrees in Celsius. The comprehensive temperature difference between side wall and bottom plate is reduced by 20 to 25 degrees in Celsius. At the same time, we applied new anti-cracking materials from Subert, developed by the team of academician Miao. Through the test, we found that the hydration heat inhibitor and the anti-cracking agent will reduce the fluidity of concrete. Their content should not exceed 1% and 5% respectively. The hydration heat inhibitor significantly reduced the temperature rise of concrete by more than 50% and delayed the appearance of temperature peaks. Anti-cracking agent significantly reduced the shrinkage of concrete from about 400 microstrain to 200 microstrain. So, the use of new anti-cracking material is helpful to cracking control. Besides the material research, we also analyzed the influence of pouring technology on concrete cracks control. Through the redevelopment of finite element software and numerous calculations, we draw the following conclusions. Through reducing the times of pouring, shorten the pouring time interval and segment length, decrease casting temperature, control temperature difference, proper curing, main structure cracking of the tunnel can be avoided. And there existed a synchronous shrinkage between the sidewall and the bottom slab. Shortening the pouring time interval, not only the asynchronous shrinkage can be decreased, but also the cracks caused by temperature difference between the sidewall and the bottom line. Finally, these calculations have been successfully used to guide the construction. During the construction of this tunnel, serious measures of temperature control were adopted. For example, substitute flake ice for water to ensure the casting temperature. Use cold water to reduce the temperature of raw materials. Drench the bottom plate reinforcement and the formwork, and set up closed awnings. After using a systematic technology of concrete crack control, as the figure shows, there's no crack occurs in the sidewall. During the construction of Taihu Tunnel, we got some useful conclusions and innovations about concrete crack control. Utilizing the hydration heat of newly powered concrete, the temperature field balance system was developed. The stress difference of the unsynchronized pouring concrete was compensated while achieving energy saving and environmental protection. The key construction technology of concrete crack control, including anti-cracking concrete preparation, temperature control, waterproof and formwork temperature in ultra-long and wide underwater tunnel was formed. As the end of this report, I will share my opinions and outlook to the technology and application of concrete crack control in super large-scale cast-in-place tunnel. Regarding the problem of concrete cracking in super large-scale cast-in-place tunnels, through analysis, we have determined that the asynchronous shrinkage and temperature stress of the concrete are the two main reasons. Combining long-wall theory and the temperature stress theory of mass concrete, we further explored the cracking principle of such structures and figured out how to take measures to control cracks. After philosophical thinking, Chinese engineers have formed the crack control concept of resistance and release. Knowledge and action are integrated in the Kong-Zhuhai Macao Bridge and the Taihu Lake Tunnel. We have developed and applied the concrete crack control technology of super large-scale cast-in-place tunnel. During this process, asynchronous shrinkage crack control technology, temperature control technology of mass concrete, balance system of concrete temperature field, application technology of new anti-cracking materials, construction techniques were formed. Combining the art of resistance and release, the cracks were effectively controlled. There will be more complicated situations in the future, and our technology research and development road still need to evolve. In terms of material, we need to continuously try to develop and apply new anti-cracking materials. In terms of design, we need to avoid unnecessary cracks through design optimization and refinement. In terms of construction, we need to continuously improve the construction process according to the working environment and conditions, and strengthen the construction quality control. In terms of monitoring, we need to strengthen the informatization of construction and control the health of concrete throughout the life cycle. I wish there's no cracks would occur in concrete structure in the future. Thank you for listening.
Thank you very much for your interesting topic, which illustrate, even in China, you are very much struggling how to control the crack. I believe this is a universal problem. I think I have received 2 questions to Professor Gu. The first one is, dear Professor Gu, I have a question which still confused me. What is the difference between this type of cracks and the cracks of other structures? What makes it so difficult to control? Probably in a large-scale tunnel and other structures, I think.
Hello, host.
Yes.
We know that the concrete mix shrinks during the setting and hardening process. If the time interval between pouring step is small, the difference in shrinkage between the bottom slab and the side wall is also small. Just like the concrete pouring in industrial and civil construction. But the key point is, during the construction of super large scale cast-in police tunnel, the limited working environment, the large section and the complex process makes the time interval very long. And the average value is 1 month. The figure of long-term shrinkage test of concrete shows that the shrinkage is basically over after 1 month. So the asynchronous shrinkage of concrete powered before and late is huge. The shrink leads to restraint, and the restraint between bottom slab and the side wall cause stress and the cracking. What's more, the temperature difference between bottom slab and the side wall is also large. As a result, their volume changes differently. At the construction joints, the thermal expansion and contraction of the side wall is restricted by the bottom slab. Then tensile stress appears. That makes crack control is very difficult. That's over, host.
Okay, thank you. Yeah, then coming to the second question from Yansui Miao. How is the concrete crack resistance safety factor defined? Why is the anti-crack safety factor higher with using the temperature field balance system? Yeah, please.
Hello.
Yes.
That's a really good question. In Chinese standard GB 50496-2009, the concrete crack resistance safety factor equals to tensile strength of 10 days C45 concrete invaded by the maximum tensile stress in the middle of the wall. Because after using the balance system of concrete temperature field, the maximum tensile stress in the middle of the wall decreased, and the tensile strength remain constant. So the anti-crack safety factor is higher. That's over, Host.
Okay, thank you. Then yes, yeah, we also have another question, but because of time limitation, I think we have to close this keynote session. Then I hope that the keynote speaker had a good presentation, and if you could have the time, you may try to answer to your questions through the Q&A session, please. So thank you very much for the two presenters. We had a very good presentation in the various aspects. So I think we move to the closing session. Thank you very much.
Thank you.